All right, so today we're going to be talking about topic 4.3, permutations with restrictions. Um, Up to this point, we've talked about a few different things already. We've talked about the fundamental counting principle. We've looked at factorial notation. And then in yesterday's lesson, we looked at what a permutation is. In this unit, we're talking about permutations and combinations. And we've talked about in previous lessons that a permutation is an arrangement of a set of elements, and order is important. When we get into combinations later, we'll talk about combinations where order is not important. Now we have this general formula here. NPR equals n factorial over n minus r factorial. And so n would be the number of elements that we have to take from, and r would be the number that we're actually picking. And so an example of this might mean that we have 15 people come out and try out for a musical. And then of those 15 people, we're going to be taking 6 of them. And so the order in which that cast list can be created would be 15 pick 6. All right, so we're going to go into some examples here. So again, a reminder about permutations. When we're looking at permutations, order matters, and often there's going to be restrictions given to us. For example, we might be arranging 5 books on a shelf, but the first book has to be blue or the first book has to be math, and so those restrictions are going to change up the number of permutations that we can have. So just like when we were working with fundamental counting principle, it's important that when we're given restrictions, we start with those restrictions first. So it says, in many problems, restrictions are made on the order in which objects can be arranged. And whenever this is the case, we deal with the restrictions first. So just the same as when we were doing fundamental counting principle. And then it says, in many situations, these problems can be solved using the fundamental counting principle. So as we go through these, there's going to be times where you see me use FCP or factorials or permutations. Again, it's important for you to know that in a lot of cases, we can use any of these methods. So example number 1, we're going to look at solving using both the fundamental counting principle and factorials. And so the first question says, in how many ways can all of the letters in the word mangoes be arranged if there's no further restrictions or if the first letter must be an N? So let's start off with no further restrictions. Now, the first way that we're going to do this is using the fundamental counting principle. And so if we count the letters in the word mangoes, we've got 1, 2, 3, 4, 5, 6, 7 letters. So that means we're going to draw 7 blanks. And there's no restrictions, so that means we have 7 choices for the first letter, 6 for the second, 5, 4, 3, 2, and 1. And again, using FCP, we would be multiplying these all out. And so if I multiply those all out, I'm going to get 5,040. Now, if I wanted to use factorial notation, anytime I'm taking a set of objects and I'm arranging all of those objects, then I can use factorial notation. And so this would be 7 factorial. Now, in the second situation, we're looking at the first letter having to be an N. And so when we set up our blanks using fundamental counting principle, again, we'd have 7 blanks. And if the first letter has to be N, there's only one way that we can have an N. And then our remaining choices are 6, 5, 4, 3, 2, and 1. And if we write that out using factorial notation, it's going to be 1 times 6 factorial, or we can just write that as 6 factorial, and 6 factorial is 720. All right, let's move on to the next example here. So it says 3 girls and 4 boys are to be arranged in a row for a photograph. And the first question is, in how many ways can this be done if there are no restrictions? So if there's no restrictions, then we just consider everybody together as a whole. We've got 3 girls and 4 boys, but in the end, we really just have 7 people. So I'm going to arrange those people, 7 blanks, just like before, 7 times 6 times 5, 4, 3, 2, and 1. Or if we were writing this in factorial notation, we would just write it as 7 factorial, which, as we saw from above, is 5,040. Now, it's not usually that straightforward. It's not typically the case where you're just given some amount without any restrictions. More often than not, there's going to be some restrictions that you have to consider. So here's a few different examples. The photographer decides that he should take a better photo, or he could take a better photo, if no two people of the same gender can sit together. And so using this restriction, we want to figure out how many total number of arrangements there can be. Well, if we look back at our sample space here, we've got 3 girls and 4 boys. And so the only way that we can alternate and not have gender side by side is to start with the boys. So boy, girl, boy, girl, boy, girl, boy, girl, boy. Okay, so this is going to be boy, 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 boy. And then the other spaces are going to be girl, girl, girl. So if we consider what our options are here using fundamental counting principle, for the boys, we have 4 choices, then 3 choices, then 2, and then 1. And for the girls, we have 3 choices, 2 choices, and 1 choice. Now we can also consider it this way. There are 7 people, but we need to have the guys and the girls alternating. So the guys can be arranged 4 factorial ways. The girls can be arranged 3 factorial ways, which gives us a total of 144. Now, if this had been the case where we had alternating genders, so we had alternating boys and girls, but we had an even number, then we would have to consider 2 cases. We would have to consider the boys being first or the girls being first. So we would have had to, for example, if we had six people, 3 girls, 3 boys, we would have had to do 3 factorial for the girls, 3 factorial for the boys, and then we would also have to consider 3 factorial for the girls, and then 3 factorial for the boys. So we'd have to add the 2 situations together. So remember, in math, and is multiply, or is add. So another question here, it says, how many different arrangements are there if all boys want to sit together? So in this case, we want all the guys grouped together. So I'm going to group them together in one bracket. So there's all of my guys. They have to be grouped together. But the girls can sit wherever they want. So girl 1, girl 2, and girl 3. Whenever we have these scenarios where we're going to have people specifically sitting together, we group them into one group and we count that as one group. So here we now have 1, 2, 3, 4 groups of people. So that's going to be 4 factorial. But we also have to consider how many ways we can arrange those boys within that group, because we could have boy 2, boy 1, boy 4, boy 3, and so on. So we consider our original group. We've got 1, 2, 3, 4 groups, but within the group of boys, we can arrange them 4 factorial ways. So we have 4 factorial times 4 factorial. And if we multiply that out, we get 576. Now the next question is how many different arrangements are there if all the boys and all the girls sit together? So that means we're going to have a group of boys and we're going to have a group of girls. So we're going to have ultimately 2 groups. One group is a group of boys, the other group is a group of girls, and they could be sitting boy girl or girl boy. So that means we've got 2 groups, so 2 factorial. But within the group of boys, we can arrange them 4 factorial ways. And within the group of girls, they can be arranged 3 factorial ways. So we would have 2 factorial times 4 factorial times 3 factorial, which gives us 288. Now again, these can be done by writing out using fundamental counting principle, but often factorial notation can simplify it more. All right, let's move on to example 3. It says 6 actors and 8 actresses are available for a play with 4 males and 3 female roles. So we've got 6 actors, and of those 6, we're going to choose 4 males. And then we have 8 actresses, and of those 8 actresses, we're going to choose 3 female roles. So the question is, how many different casts are possible? So So we're going to look at this using two different methods. We're going to use permutations, and then we're also going to use the fundamental counting principle. So with permutations, we have 6 actors. Order matters when we're creating that cast list. So we've got 6 actors. We're going to pick 4 of them. And, so and means multiply, we have 8 actresses, and we're going to take 3 of them. So 6 actors, picking 4 of them, and then we have 8 actresses, and we're picking 3. So I'm going to just write this out here. So we've got 6 actors, we're picking 4, and we have 8 actresses, and we're picking 3. Well, if we multiply that all out, we will get 120,960. So 6 pick 4 would be 360. 8 pick 3 is 336. And that gives us a total of 120,960. Now, using the fundamental counting principle, we would look at our cast list, which would be 7 people. 1, 2, 3, 4, 5, 6, 7. And we have, for the males, 6 choices, 5 choices, 4 choices, and 3. And then for the females, we have 8 choices, 7, and 6. So we can multiply these out. Notice we can't use factorial notation because we're not taking everyone and arranging them. We're just choosing a select few. So if we multiply this all out, we will also get 120,960. All right, so we're going to look at an example here where someone has tried solving the problem. They've given their explanation, and we want to see if they've done it correctly. So it says Janine was asked to determine the number of arrangements of the letters of the word brains in which the vowels are together. And so we just talked about that in the last group, where we're going to take those vowels and group them together as their own group. And she lists her reasoning here as below. It says, since the vowels must be kept together, I will treat the A and the I as one element. And this means I now have 5 elements instead of 6 to be arranged in order. The 5 elements, AI grouped together, B, R, N, S, can be arranged in 5 factorial ways. So my answer is 5 factorial equals 120. I want you to take a moment and think about that and ask yourself, is she correct? First of all, is she correct in saying that A and I should be combined as one element? And then secondly, is her final answer correct or not? Well, I actually tell you here that her answer is not correct. So I want you to tell me or decide for yourself what's missing. What did she do wrong? So pause the video, think about it, and then come back and check your answer. Well, first of all, Janine is correct in grouping them. We just finished talking about that on the last page. If elements have to be together, then we group them together. But the reason that she's not correct is that she hasn't considered that AI can be written as AI, or it can be written as IA. So when we count those groups, we have to count AI as one group, and then the B, the R, the N, and the S. So that gives us 5 groups, so 5 factorial. That part was correct. But we have to consider that the A and the I can be arranged in 2 factorial ways. So 5 factorial times 2 factorial gives us 240. Now, the reason I mention that is because this is quite a common mistake for us to consider our groups and then miss the arrangements within the group. All right, so it's just a note down here. It says that whenever items must be together, we treat them as one element. But again, you might want to make a note for yourself. You also have to consider the number of arrangements within that group. All right, so we're just going to keep going through a couple more examples here. The next one says, find the number of permutations of the letters in the word Kelowna if the letters K, W, and N must be together and they have to be in the order K, W, N. So whenever I'm working with words, I find it easy to, or helpful to write out the scenario. So K, W, N has to be together, and that's going to leave me with E, L, O, and A. And I don't know about you, but sometimes when I'm doing these, I have a tendency to miss some letters. So I'll always go back and double check that I've got everything I need. There's a K, E, L, O, W, and A. I have all the letters for Kelowna, so I'm good to go. Now, if I count this out, I've got 1, 2, 3, 4, 5 groups, 5 factorial groups. And I guess you could technically say there's only one factorial way to rearrange these, but since that's just times 1, we can leave this as 5 factorial, which is 120. Now, the second scenario says that the letters K, W, and N must be together, but not necessarily in that order. So again, I would write out my letters, K, W, N, and then E, L, O, A. There's 1, 2, 3, 4, 5 factorial ways that I can arrange those groups, but the KWN can be rearranged within their group. So now there are 3 factorial ways to arrange those letters. So 5 factorial times 3 factorial is 720. And we're going to look at one final example here. So Aiden, Jeff, Hannah, Ida, Greg, and Kyla have playoff tickets for the Tigers home game in adjacent seats A3 to A8. And the first question is, in how many different ways could they sit together in those seats? Well, if we count, we've got 6 people, and that would mean 6 seats. So 1, 2, 3, 4, 5, 6. So we can use fundamental counting principle. That would mean we have 6 choices, 5, 4, 3, 2, and 1. Or we can write this out in factorial notation because, again, we're using all of the people and arranging them. So 6 factorial would be 720. But things aren't always that easy. Usually there's some type of restriction. Well, in this group of friends, Greg and Hannah happen to be dating. And so the question is, how many arrangements could we have if Greg and Hannah have to sit together? And so just like before, Greg and Hannah are going to be their own group. And then we have all the rest. We have Aiden, we have Jeff, we have Ida, and we have Kyla. So how many ways can we arrange them that they're sitting together? We'd have 1, 2, 3, 4, 5 factorial ways. And then we can either have Greg and Hannah or Hannah and Greg. So there's 2 factorial ways for them to arrange themselves within their own group. And so that leaves us with 240 ways. Okay. Now, right before the hockey game, Greg and Hannah got into it. They had an argument and they decided they can't sit together. So the question is, how many arrangements could we have if they refuse to sit together? And so this is one that I'd like you to put a huge star by, because these are the questions that most people will often mix up. When we are dealing with questions where 2 people cannot sit together, or 2 people cannot be beside each other, or 2 objects cannot be beside each other, we take the total ways with no restrictions. So the total with no restrictions, and we subtract the ways they can be together. So we take all the ways we can arrange the objects and subtract all the ways that those objects can be together, and this is how we get the number of ways they are not together. So we knew from before that there were 720 ways for these 6 friends to arrange themselves. So that would be 720 minus the 240 ways that the 2 have to be together. And that's going to leave us with 480 ways that the friends are not going to be together. So I'll give you one more example. It's not written in your notes, but just so that we can get a little more clarity on this. So we're going to talk about some family photos. So imagine going for family photos, and we're going to have a family of 5. So we're going to have family photos, and we're going to have 5 people in the family. But in this family, we have a set of twins, and those twins don't get along very well. And the parents have decided that they cannot be standing side by side because the photos just aren't going to turn out. So we have this scenario, and we have a question about how many ways can we arrange these photos if the twins can't be together. Okay. And so we ask ourselves first, how many ways can we arrange those 5 people? Well, we can arrange those 5 people 5 factorial ways. How many ways can we arrange them so that the twins are together? Well, we'll just write out A, B, C, D, E. Those will be our 5 family members. And A and B have to be together. So that's going to be 1, 2, 3, 4 factorial times 2 factorial. So there's 4 factorial ways to arrange those people if the twins have to be together. So how many ways can they not be together? Well, we take our total and we subtract the ways they can be together. And that gives us the ways that they aren't going to be together, which in this case is 72. So those are just a few examples of permutations when we're dealing with restrictions. The next step after this is going to be to look at permutations with repetition. So we'll have restrictions and repetitions as well. Again, if you noticed up to this point, we have not seen anything with repeating letters or anything with copies. And so that's where we're headed next. All right, thanks guys. Have a great night.